Welcome, everybody. Today we're here for the Steve and Sylvia Burges lecture by Jessica Lundquist. And my first thank you goes to Steve and Sylvia Burges for making this lecture possible. This lecture series started in 2013, and it's basically to kind of showcase the work being done by civil engineers. But it goes beyond just the technical problems associated with civil engineering.
I'm Professor Jessica Lundquist, and I am recording from Davos, Switzerland.
I'm really glad to be able to introduce this year's speaker, Jessica Lundquist. Jessica got her undergraduate degree from Davis in atmospheric sciences, and then got a master's and PhD from Scripps in oceanography, although her work was actually looking at mountain streams. After that, she went to Boulder and was there for 2 years as a postdoc and joined our department in 2006. Over the last decade and so on, I have had really the opportunity to work with Jessica quite a bit and see how she kind of mentors her students and her research group. And I've really kind of admired her generosity and her mentorship for her students. She also, over that period, has developed into being one of the preeminent snow hydrologists in the United States. It was pretty amazing this past fall when she actually won a number of awards almost simultaneously. It was an ambassador award from the American Geophysical Union, which is an organization of about 60,000 members, and only 1 to 5 people a year are given that award. As part of that award, she's then also inducted as an AGU, American Geophysical Union Fellow, and at the same time she was also awarded by the American Meteorological Society the Horton Lectureship. And so she actually gave a lecture at the American Meteorological Society meeting in January, where she actually gave this presentation. And so we thought it would be great to actually have her give a version of that for us, which kind of was part of the impetus for awarding her the lectureship, the Steve and Sylvia Burges lectureship. So I will leave it at that. Jessica, please take it away.
All right, thank you so much, Bart, for that wonderful introduction. And I also want to extend a thank you to everyone who brought me an HDMI cable. One thing I really like about UW is that even though things break frequently, you always have really good colleagues to come to your rescue, so thank you. So I'm going to talk today about patterns in the peaks. And this is a picture right here of my favorite watershed in the world. All my students know this. This is the Tuolumne watershed in the Sierra Nevada, California. And before I begin, I want to extend a special thank you to Steve and Sylvia Burges for their generous support of the department and of me over the years. I happen to have an office right next to Steve's. And I really appreciate their love of both mountains, this is them near Lake O'Hara, and of music. And you'll see those themes coming through my talk, that we're kindred spirits here. All right. So mountains are the water towers of the world. And this is a little bit busy picture, but what's shown here is all the mountains of the world that are critical water supplies to humans. And sort of these red colored areas, this was a graphic put together by Steve Margulis and the JPL team in an effort for a snow mission to say, like, these are all the areas where we need to know how much water is stored in the mountain to provide water for people downstream. We call these, like, this is 3 billion people in watersheds. And then here's just a picture of the mountains from watercolor by Matthew Sturm and a picture of Lake Mead in Colorado, which is the poster child of trying to catch mountain water and give it to people. But how much water is there? This is just a red color. Can we put some numbers on this? And so as part of this effort, we tried to do this. And there's, again, a lot here, but I want to focus on, okay, 3 major regions. Here's the Western US, here's high mountain Asia, here's the Andes. 1 kilometer cubed, just to put it in perspective, is 0.8 million acre feet. And when I think about that, I think, okay, that's millions of football fields filled with a foot of water, or maybe 1 football field with 1 million feet of water, whichever helps you give a bigger concept of what it is. And I want you to look at these spreads. So over here in high mountain Asia, factor of 10 difference is like number of football fields filled with water of what's up there. Western US, factor of 6. Are we really, like, how much water is there in the mountains? And if you scan the literature, it looks like it's a huge mystery. So I want to give you an outline of what I'm going to talk about. If anyone's in the back wondering if they want to stay, this is your chance to leave. So first I'm going to talk on drawing from lessons from Steve Burges. We're going to think about the whole water cycle in the context of the snow problem. We're going to focus on the western US because this is where we can actually pin down some of these numbers. We could live here, we can go dig in the snow, we can make sure we know what we're doing. I'm going to talk about the history. Snow-fed streamflow is really critical to agriculture, and that's what's driven a lot of the work out here. And I'm going to explain why there's some problems. Mountain snow is highly variable. It's hard to measure. Mountain precipitation is hard. Snowfall is even harder. And errors in snowfall are magnified when we try to account for total snow accumulation. I will show you that snow predicts streamflow. Streamflow can help assess our understanding of snow. And rather than being overwhelmed by all this variability, we can actually make sense of it through coherent patterns. And understanding these patterns will let us know what's going on. So let's start with lessons from Steve. This is a picture of Steve in 1967. I believe it was 22, is that about right? And this is also as learned by Jessica. I've learned in teaching that sometimes like what you think you're teaching is not what people learn. This is what I learned. Steve may have had other objectives. Number one, read the literature. Smart people figured out a whole lot before you were born. Number two, question everything, particularly precipitation measurements. Number three, look at your problems from many perspectives. Check out the details, and then go read the literature again, because you probably missed something. All right, so let's start with the hydrologic cycle. You start with precipitation. It falls on the ground. You have some storage, often snow storage. Some will run off, some will evaporate back to the sky. This should all balance. There's some things here you can't quite see with these extra things. What Steve often says is, you know, I'm a simple bloke. Hydrology is really just about adding and subtracting. So we're just going to try to do that today. This is our key equation. All right. And just for mine, this is mountain hydrology. We're just going to focus on a simplified version of it today. Precipitation is rainfall plus snowfall. Stored as snows in the mountains leads to streamflow and runoff. All right, so snow storage. Again, that problem I showed you to begin with, how much snow is there in the mountains? This is a paper from Mortimer in 2020 in the cryosphere, looking at the whole northern hemisphere. Upper left hand is a reanalysis mean from a number of different model measurement combined products, and then these are 3 satellite-based products. You will see SWE as a term means snow water equivalent. This is the depth of water you would have if all the snow melted. And this is the mean for winter months for about a 7-year period. Now, let's just zoom into where we know, where we live, western US. Okay, here's reanalysis mean, which is supposed to be the best guess. 20 centimeters of water in Washington, 2 centimeters in California, and 8 centimeters in Colorado. Anything wrong here? Okay, we are going to answer this question with a field check. So this is winter 2025 UW snow hydrology class, right? We're going to send them up in the mountains, go see, do we have, 20 centimeters of snow? So this year was a slightly below average year. So, we should be somewhat close maybe to this average. Also, SWE is the water. You need to multiply that by the density. So about for Washington, 40%, 20 centimeters, we should be measuring about a 50 centimeters of snow depth when we go look up at Snoqualmie Pass. All right, here they are working hard. There's a lot of digging. Here is the measurement here. Right there, it says 160 centimeters of snow. For reference, I am 160 centimeters tall. And this is 3 times as deep as the mean reanalysis estimate. You can fit your entire class in a snow pit in Snoqualmie Pass almost every year. This is a kind of warm site in Washington. It's not the most snow anywhere either, right? Looks suspicious. All right, so what's the problem? Why are these global products having so much difficulty? One thing is, Western US, living in Washington, this is a really easy thing for most people here to grasp. When I talk to people from the East Coast, they say what? What are you doing out there? Things are really smoothly varying on the East Coast. And you look out here, and Washington, I like to say that the color purple is UW and is reserved for rain in Washington, right? Only Washington really gets up to the purple color bars here. So here in the Cascades, 100 inches for average annual precipitation. It's 8.3 feet, 2.5 meters. right next to eastern Washington where there's almost none. Colorado, 40 inches, 3.3 feet, 1 meter. And just for comparison, one of the wettest spots on the eastern US, 70 inches, 5.8 feet, 1.7 meters down here in Louisiana. So it's tricky where there's so many contrasts in what's going on. Coarse resolution doesn't work so well. It's not only variations in space, but it's variations in time. So what you're looking here is, this is from the US Environmental Data Service. This is a graph that Steve gave me long ago that I used many times. And each one of these shows month of year in inches of water. Here's Seattle. And again, if you live here, that seems normal, right? It rains all winter, it's sunny in the summer. Also in California. But you look on the East Coast, it's about the same all year round. So we have this really different temporal pattern. And summers are dry, it's when we need water for agriculture. So despite this winter precipitation, streamflow peaks in the spring and summer. This is a book that Steve gave me, The Water is the River in the Rivers and Creeks by Langbein and Wells. And you can see here is from the prior graph, timing of the rain. Here in the western US is a timing of streamflow. The streamflow is delivering the water in the summer when we need it. And that's because over 50% of our water supply in the western US comes from mountain snowpack. This is a view out the airplane window of Yosemite National Park. And Horton, Bart mentioned I gave the Horton lecture. In 1934, went and studied the mountains, following the Read the Literature lesson. The best and often the only economic use of high mountain areas is to provide water for downstream areas. Those of us who like hiking might disagree, but. And so here you can see that. These are two rivers in California, the Merced River in the mountains in Yosemite that I showed you the picture of. Smith River is on the coast and gets only rain, no snow. So the Smith River has streamflow when there's rain, and the Merced River has streamflow in the summer when there's no rain. It goes without saying, food grows where water flows, and this is supporting western US agriculture. The other thing is that the amount of water in the streams in the summer for agriculture varies drastically. This is just 2 years. They're not even the most extreme years. California actually has been making the news that this is almost a normal year. It is never a normal year in California, so it's really big news that they actually have an average snowpack this year. So here's streamflow. This is discharging cubic meters per second. And to give you an idea of how much is a cubic meter per second, this gauge happens to be right below this waterfall. It's a nice gauge to visit. And the difference in this is about 4 cubic meters per second between these two waterfall pictures. And the difference here is about 20 or more times that, right? So these are huge variations in water coming down the river. And there's variations in timing and amount. The water is over allocated, and so how much you get depends who is going to plant what for agriculture. Being able to predict what will come down is worth a lot of money. This has been true for a very long time. Going back in history, in 1909, this guy, James Church, who is probably the father of Western US snow science, who surprisingly was a professor of Greek and Latin at the University of Nevada, Reno. If you read his papers, they're beautifully written. They're very nice to read. And in 1909, he started sampling snow up here on the top of Mount Rose. You can see it right here. It's kind of like Lake Tahoe on the border between California and Nevada. And at first, he just thought snow was cool. He was kind of an outdoor enthusiast and went and started measuring everything about snow. And after 1 year of doing this, the Sierra Pacific Power Company asked him to please share his data so they could use it to forecast the stream flow. And what he wrote was, it was quickly seen that the winter snow in percentage to its normal equaled that of the summer rise of the lake. And rivers followed the same rule, but more closely. So after only 2 years, he was forecasting amount of water in the lake. It was critical because the wet side is over here, the dry side's over here. The Truckee River drains towards the dry side, and everybody over here needed to know how much water was in that river. Now this led to the start of the Western US snow surveys. So this is a circular from 1953. In the 1930s, which is in conjunction of the era of big dam building, the snow surveys really started all across the Western US. Everyone managing these reservoirs needed to know how much water was coming into them. And by the 1950s, they were very successfully forecasting stream flow from these snow observations. So you've got this is a picture of what they do. This is also what the students were doing with Johnston Barris up at Snoqualmie Pass. And here's streamflow on the x-axis, snow storage on the y-axis. And what I want to highlight, it's a little bit hard to see, but this is the air bounds. This regression from the snow course to total runoff from April to September in the 1950s had 10% air bounds. So, you look at snow accumulation, the volume of snow that accumulates predicts the volume of summer runoff over here. So, and here's just a picture of one of these. This is a snow pillow. It just weighs the weight of the snow. Here's a precip gauge. It's incredibly tall because it needs to be above the snow. There's some weather instruments up here. That's another precip gauge. And here you can go in real time. This is from just a day or two ago, and you can see how is our snowpack doing. You can see Arizona is really not doing well, significantly below average. You're above average for this bit in Oregon, and then I think Danny said this is not popcorn, it's a Skittles snow. It looks like your whole set of Skittles. Washington, we're kind of slightly on average slightly below average, but there's a wide variation where the lower, warmer sites have a lot less than the higher, colder sites right now. Okay, so let's go back. Okay, so despite this historic forecasting skill, our current estimates of the snow water storage really disagree a lot, as I showed you at our very beginning problem. So what is the disconnect here, right? In the 1950s, streamflow is predicted with 10% accuracy from just some point measurements in the mountains, right? These are some people going and sticking sticks in the snow, and if, nowadays we take measurement at a point. This is all kinds of models and reanalysis, and it's, varying by a factor of 6. And these values over here are ranging from not enough water to fill Lake Mead in Colorado to enough to fill it 5 times. So what's going on? First, you should just rest assured that Lake Mead operations are using the snow surveys, so they are operating fine, and they generally can give you a decent estimate of how much water will fill. Not always, but much better. They're more in the 10% air bounds most years. So then, how did this range get so large? So let's ask Steve Burges and Robert Horton for help. So lesson number 2, be skeptical, especially of rain gauges. These are a number of Steve's papers over the years, and those of you who've been here for a while might remember he had a plot over at the Horticulture Center where he had a regular rain gauge and one buried, and found significantly more water was collected by the buried rain gauge due to undercatch, due to wind around the other one. Now these problems he was observing are nothing compared to what we get when we go to snow. So here's Horton in 1934, and he was going up sort of near Aspen, Colorado, and found the annual runoff was up to twice the amount of annual precipitation. He actually has a very interesting discussion in there where he's wondering whether the mountains just harvest water out of the air, right? Because it clearly isn't falling in the rain. I finally decided no, it was kind of dry in Colorado and it was evaporating, but these are the numbers where the difference between runoff precipitation was negative. Concluded that we can't catch snowfall. And indeed, many other people have concluded that with time. It's incredibly hard to measure how much snow falls. Yeah. On top of this, as you go up in elevation, we have very few measurements of any kind. Here's elevation on the x-axis, going to higher elevation, number of stations. This is a graph from California, but you could plot it almost anywhere. You got lots in the valley as you go up. It's just hard to get to. Similarly with radar, mountains block radar, so we don't see rainfall or snowfall. And snow on the ground is substantially easier to measure than snowfall, but it's incredibly varied in space and time. These are pictures from Matthew Sturm that are just really a few feet apart from each other in Alaska. Here he is in a snowdrift, and then this is basically as deep as the palm of his hand over here. So if you make one measurement, what does it represent anyway? Even going to the places where these are locations with those snow pillows I showed you that they're using to forecast water resources. The dot is where the snow pillow is, and the colors are showing you snow water equivalent around it. So it varied by almost a factor of 2, by a factor of 3, by a factor of 4, by a factor of almost 10 over here. So if you moved that snow pillow, it would give you a totally different number. And this is just from a snow field campaign. Again, 2 nearby sites. One is, I could stand there and it's taller than I am. And this is one where Carrie dug her snow pit so fast, she got bored and had to make an ice sculpture. So satellites, right? Satellites have potential, but one thing to notice with satellites is that deep snow, wet snow, and forests all thwart current sensors. So this plot over here is showing you some different sensors. It's showing you how deep of snow it can actually sense and how much forest canopy it can get through. And those of you who've been up in our mountains can say, well, yeah, deep, wet, forested, that's kind of our mountains, right? So for satellite-based retrievals of snowfall or snow on the ground, please read the fine print. A lot of these are biased very, very low, particularly where there is deep snow. Okay, so that wasn't working out. Like Horton, let's check streamflow, right? So, okay, this plot was made over this area, the entire western US, this plot aggregated together. So in this area, the major snow-fed basins are Columbia, Sacramento, San Joaquin, and Upper Colorado River Basin. So like any good scientist, you scour the internet, right? What does Wikipedia and Google say? Typical annual discharge is Columbia River, 244, Sacramento, San Joaquin, 7, Upper Colorado River, 18. Like Steve Burges, we're just gonna use some adding and subtracting, 270 cubic kilometers of water coming out in the stream. Let's be generous and presume 50% of that is from snow, okay? 135, let's draw that line right here. Remember, Horton confirmed that there is evapotranspiration in the mountains. They're not just condensing water onto the ground and into the stream flow. So you can see right away that some of these plots look much more plausible than others. All right, so with all these challenges, you might understand why there was all these scatter in the plots of snow water storage. But then how did the snow surveyors make this work? What's the secret? This is Mount Rainier. So my son goes to music lessons and is just starting to learn the trumpet. And he asked his teacher, he said, there's all these notes, and how does anybody do this? And you play them fast, and you play lots of notes at once. And he says, well, the more music you do, the less you perceive one note at a time. You start seeing patterns. You see chords, you see progressions. You see, if you play on the piano, spacings of your fingers that are the same over and over. And these patterns let you reveal things in the music that you wouldn't get by just one note at a time. And so this one, those of you who are musical may have noticed, it's the snow glows white on the mountain tonight, right? It's singing about snow. So mountains create that organization and structure. There are repeating spatial patterns in the mountains, and they are ubiquitous. This is from a paper by Matthew Sturm and Anna Wagner. And what this is the Mountain of the Holy Cross in Colorado, from a painting in 1875 by Thomas Moran, a picture in 1873, and a modern photo in 2004. And you can see that year after year, the snow makes the same cross right there on the mountains. And it's not just that cross. In Japan, you can sign up for a special tour in the spring to go see the Yukigata, which is a word that means the shape of the lingering snow on the mountainside. And here in Montana, Eric Sproul sent me this photo taken by Mike Roberts, and he says this is the butterfly in the Pintler Range. And the ranchers say that when the wings of the butterfly separate, they know they have about 2 weeks of good water left. All right, so there's these patterns. So why? Why are we getting these patterns? It's because in the western US, the story starts over the Pacific. And we have these warm water from the tropics of the Pacific Ocean that deliver the majority of water to the western US in these narrow plumes of moisture. This water vapor is then blown over the mountain. Mountain precipitation is usually proportional to the amount of saturated water vapor blown across the mountain slope and the steepness of the slope encountered. You just lift the air, the water vapor condenses, you get the rain. This is fairly well described in linear theory back to the 70s. And this is why we have a wet side that's where the air is lifting, and a dry side where the air is sinking, and places that consistently get more precipitation than others. Also, the mountains block, deflect, and extract precipitation. So specific moisture funnels through these gaps in the mountains, creating coherent storm patterns throughout the western US. This is a paper from Alexander et al. You can sort of see cross-section topography. This is how the storms get through to the interior. And this creates, repeatable patterns in different years of where there's precipitation. And for those of you who recall that snow pillow map, look, see this blue where there's extra moisture? See the red right there? That's our pattern this year. All right, and in general, the total snowpack in most of the western US is built up of only a few of these large storms. There's other tiny storms, but they don't make up a whole lot of the total. The total is from a few really big storms that often have very similar characteristics. And while individual storms may vary, the sum of these storms ends up with similar trajectories, similar deposition patterns of snow, and similar spots where there's more and less snow on the landscape each year. In fact, if you go, and here again is another snow survey, and California has been doing this since the 1930s. This is just an analysis from 1950 to 2010 when there were a lot of stations. And an EUF analysis is something where you look at the data and you say, okay, what's the dominant mode of variability? What makes things go up and down? And it says the dominant mode is that everything goes up and down together. It basically is saying that in California, 96% of the variability means all of California is wet, all of California is dry. If you measure even one of these, you've got like 96% of the variability for the state of California. A lot of people ask me, well, what about, there's no trend in that. The trend is actually in the second one. This is what those of you might remember, there was a paper in 2005 by Phil Mote looking at observational trends in snowpack. And it showed that the warmer northern Sierra was going down in snow, the upper was going there. It's only comparison to 96% of the variability, 1.2%. It's much smaller. So the interannual variability is for water resources, the biggest thing to worry about. As long as the wind directions during the storms come in the same way, you also get patterns at very fine scales. So you can see that on the top, there we go, is this working? There we go. On ridges, you get erosion, and downstream of ridges, you get deposition. So even microtopography will govern where the snow is deposited. So those drifts that Matthew Sturm was standing at that were right next to each other in Alaska could be predicted by wind direction and microtopography. And multiple papers have found that snow patterns repeat themselves year after year. This is a picture of trees where the wind comes from this direction, and you can see that there's snow drifts just downwind of the trees. Again, year after year. So, all right, I've showed you the entire Sierra Nevada correlates together as wet or dry in a given year. But do the same places really at a fine scale always have more or less snow? So this is some work by Justin Flug, looking again at the Tuolumne River. That was that first picture I showed you in Yosemite National Park. And we're just going to look at a few subdomains here. And we're going to use a really cool data set called the Airborne Snow Observatory, which has been flying LiDAR over the Tuolumne watershed since 2013. I actually remember when it started, and it's excited. It's been, almost 15 years now, 12. So what it does is the plane flies over a LiDAR pulse, reflects back from the ground, and then you fly again. When there's snow on the ground, take the difference. It gives you the snow depth everywhere at about 3 meters resolution. So Justin took this data, and he looked at 4 different years near the time of peak snow water equivalent, so the most snow on the ground. And you can see that the amount of snow in these years varied drastically. 2005 was about the driest year on record, almost none. And 2017 was one of the wetter years, 4.5 meters. So in terms of amounts, they're drastically different. But if you took these and just for each one divided by the aerial mean, all of a sudden you get, for the 3 different domains, these 1, 2, 3 sets. And then this is for just 4 years for one of the domains. Again, red is shallow, blue is deep. You see that where it's shallow and where it's deep is the same year after year after year. The spatial coefficient, 0.8 to 0.91. All right, so to summarize, these are my students being very happy taking snow measurements at Crystal on a perfect day last spring. So peak snow accumulation near April 1's, time of April 1 snow survey. This is when James Church went and took his mount to forecast the water in the river. They have spatial patterns that are repeatable year after year. This means that in index measurement, you go to one spot and it gives you a measurement relative to other years of every other spot in your watershed, which tells you the basin-wide runoff total. This index measurement also indicates specifically where the snow is, so you could actually distribute. You could distribute a coarser resolution measurement or distribute one point measurement all over the watershed. So we can also downscale coarse resolution model data over our watershed and put the snow in the right places. This already exists. This is just a sampling of papers. You could do this via pattern matching, via machine learning, via physically based model. These are tools we have right now once we realize we have these patterns. Okay. All right, so we've got our snow accumulated. What about snow melt? Does everything just fall apart when the snow melts? This is a picture from my husband took in the Washington Cascades. There's just breaking up the snow melt. We were sliding down the hill and trying to avoid the water. And at this point, the energy balance determines when snow melts and streamflow begins. So I talked about this amount of storage, gives you the volume here. The energy in the spring, how much you have of energy balance, snow temperature, will determine the onset of streamflow, when it starts going. Now, in terms of patterns here, what is exciting is that large rivers rise and fall together. So large-scale weather patterns are controlling the timing of the rivers. So here is the spring onset of a number of river basins. This is all across California, but Dave Peterson and Dan Cahan, about the time I was working on my PhD, showed this was true for the entire western US. And this is exciting because it means everything turned on at once. This is in Yosemite Valley. This is like a slush flow of ice and water all moving. I didn't put in the soundtrack, but it's amazing. If you're in there, we've got ice going over a waterfall. And who can tell me what music we've got up here now? Come on, looking at the cherry blossoms, you all must be humming it. Dun 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 dun. It's Vivaldi's Spring, right? I mean, it's the symphony. So in general, temperature decreases with elevation. So we would expect the lower elevation snow would melt first. This is sea level and average decrease 6.5 degrees C per kilometer here, colder at higher elevation. But in some years, these synoptic weather patterns that are changing from warm to cold are so large that they bring a warming of 12 degrees C at once that overwhelms anything in that lapse rate. That basically it's enough to switch everything. This is a year in California where temperature looks like a light switch, right? Okay, now it's summer, now it's winter, now it's summer, right? And that means everything turns on at once. This was spring 2002. I had been working my PhD thesis, thought I was going to see the differences between all these streams I worked so hard to put gauges in, and they looked all exactly the same. I decided that was exciting in and of itself. And it also, how many people have read The Emerald Mile? A few? It's a good read if you haven't read it. It's talking about this year in 1983 in the Colorado River, when it was what I call a synchronous spring. And in 1983, over 20 snow-till stations in the Colorado and Wyoming, it was a really, really late year. They had a lot of snow. It kept snowing. Then all of a sudden, it was one of those light switch. Everything warmed up at once. Everything started melting at once. Then it didn't stop melting either. And it ended up, this was the year they had to put up boards to keep the Lake Mead from overtopping. And the story here is about people running the Colorado River when they ended up having to release a whole lot of water. But it goes through what was going on at Lake Mead too, and it's a fun read. Okay, so we've got spring started. Now we can switch to summer and the decline of the hydrograph. Now the decline of the hydrograph depends on the snow duration within the watershed. How much snow do you have left up there and how long is there still snow. This becomes really critical here in the Pacific Northwest because this is what the salmon need to get up the stream. And if you look here, these are the same streamflow hydrographs. This is the amount of water coming down. This is time for a number of basins in California. You can see this is the first part of spring. They're all in perfect sync, right? This is controlled by the synoptic weather systems. And then you see by mid-June, they're doing something different. You can see these two with a dashed line are lower elevation basins. You can see that because they got rain right here. And they had less snow. And you can see that the water is running out there much sooner than in other locations. So the amount of snow matters, but its duration. And the duration of snow actually depends on its distribution in the watershed. It depends on snowpack heterogeneity. Now that's a kind of word people throw around there. What do you mean by that? So here, if we have uniform snow, we just put snow of the same depth all over the snowpack right here. And then over here we have the same amount of snow, but I've just put it in two snow piles. Now snow insulates itself and it melts from the top. And so we just melt half the snow here. Now we have about half the depth of snow, and one of our snow piles went away. We have one snow pile. We just repeat that again. Now all our water's gone. But in that heterogeneous snow, we have water lasting longer into the summer. Now, if you put these deeper snow piles in shadier locations, this lasts even longer. Now, the snow disappearance not only is important for that late season stream flow, it also predicts wildflowers. So this is Mount Rainier. This is some work I did with a number of students in the biology department. And if you want to go hiking, this is the best scatter plot I have ever seen in ecology. You can predict peak flowering based on the day of snow disappearance with amazing skill. These flowers just wait for the snow to go away, and then there's just a delay in number of days, and they all pop out. So if anyone wants to go hiking Mount Rainier, we could help you. And we can make, based on these repeatable snow patterns, really fine scale patterns. This is work by Nicoletta Cristia, who's somewhere in the audience. I lost her. There she is, right there. You can ask her questions later. So she, using these patterns, right? Snow sits longer in shaded depressions, right? We talked about the wind, blows it into the depression off the ridges. Shade's gonna make it last longer. Snow is also gonna disappear first from a steep ridge because snow fell off it, and it gets more sun. And so she could downscale very coarse resolution satellite data for very fine scale patterns that would predict exactly how the snow would go and when the flowers would appear. You can see they appearing right here on the edge of the snowfield. It really is just a matter of days since that snow is gone. So with all this knowledge and all these patterns, do we actually know how much snow is in the mountains? From stream flow, the higher estimates here really are more likely correct. Also, Brian Henn has a work of data that showed in California specifically, many precipitation products and snowparks are just way too low. Almost everything is biased low in mountains in terms of snow. And so the highest ones are the most accurate. But we can also use what I showed you in Tuolumne. That airborne snow observatory has been flying a lot of watersheds across the West. And this is work in progress by Darren Jackson, Mimi Abel, and William Ryan Currier at NOAA. And over here, I'm gonna wear this out. There's a number of basins across Colorado where they were looking at how much did this LIDAR, which is a very reliable amount of snow depth, compare to this set of products. And so here's just a comparison for one river basin in Colorado. This is the mean of 17 flights that took place between 2016 and 2021. This is for one basin, and so what they did was they took the average from all the flights, and then they corresponded all the products to that exact day, and clipped it, and summed how much snow does it say it is in this basin. And the first thing that you can see really for all these different products is just the resolution, right? You can see the huge variability in the snow as mapped by the LIDAR. And then you can see that as the products get coarser, they have a harder time. We can summarize it, and you can see that here too, ASO, which we're calling truth, has the most snow. And this GLDAS with VIC really does not have enough snow. Now, how these products compare to what we did before, this GLDAS VIC was this line right here. All of these were considerably worse, and Darren didn't plot them because they had 0 snow for this particular basin. So the one thing is, based on both streamflow and aerial LiDAR, the highest volumes are correct, which means that the mean of the data set is wrong. One thing we often do in science is we say, I don't want to pick favorites. I will just, all these different groups made different products, and I'll just take the mean of them. That's going to be my best estimate. And in the case for snow, they are biased, and the largest ones are right. And if you just take the mean, you are incredibly wrong by almost a factor of 2. So what can we and should we be doing now? So just to summarize what I've said, topography shapes the meteorology from the precipitation to the energy available to melt snow. Repeatable spatial patterns let us downscale coarse resolution models, and they let us map from a single point measurement to entire watershed. Putting snow in the right place is key to the snow duration, that late season stream flow, which is important for our fish and for our wildflowers, so for ecology. New technology is letting us make these maps at very fine resolutions with very high accuracy. There are progressively more and more high resolution satellite projects that tell us where snow disappears. And this can be used to figure out how much snow must have been in this spot to keep snow that long on the ground. Airborne LiDAR maps are also making snow depth maps at meter scales that we can use to diagnose patterns and understand how good we are at other products and what the baseline pattern for a place might be. Now, patterns lend themselves to machine learning, right? Anything you see a repeatable pattern, a machine should be able to do this. But I really want everyone to remember the caveat that and if you just randomly picked one of those products off the shelf, you might be training your machine to match the wrong thing, right? Not all snow products are created equal, and the mean of all the products, or at least for the Western US, is incredibly wrong. So we need to be brutally honest about where and when our satellite products are working well and when they don't. Right now, we don't have a dedicated snow mission. David's working on something for the future, hopefully. And existing satellite sensors give us partial and often biased information. Once we put the patterns in place, what should we be working on? I think we should focus our attention on what causes the patterns to break down, right? Those regressions on the snow survey that they're using to manage Lake Mead do break down in some years. I mean, they're not as bad as the factor of 6 difference, but they're problems. This is a picture from California in 2015 where they had no measurement, right? There was no snow for the snow survey. And this is from a recent paper by Danny Hogan that said, okay, look, with our precipitation anomaly up till 2000, we could predict the color of our streamflow anomaly. After 2000, we couldn't. The patterns shifted. And what changed was the frequency of spring precipitation, which actually, when it got sunnier and not cloudy in the spring, those flowers came out early. All the transpiration really lost more water than we expected. So with that, I would like to say thank you. This is a photo of the location where Horton was doing that study that lost all the water, and it also happens to be a location we did a field campaign a few years ago. And thank you very much.